Hi guys, a couple of quick examples, or I hope they're going to be quick, of where we combine the various rules of differentiation. We use more than one rule in each exercise. So here we've got something that really does look like the product rule, I hope, because you can see two distinctive parts there. That part might be considered U, and this part might be considered V. Now, of course, when we find the derivative of V dash, we're going to need the function of a function or chain rule. So that's why we're combining the rules when performing a differentiation. Okay, so let's proceed. U is equal to, well, obviously 2x squared minus 4, which would mean that U dash equals 4x. Okay, and V is equal to 3x plus 5, all raised to the power of 6. And the derivative of that, of course, is bring down the 6. Write down what's in brackets, which is 3x plus 5. Lower your index by 1. And then times by the derivative of what's in brackets, so that's 3. Okay. So, as the pattern says, we need to do uv dash plus vu dash. So it's a cross multiplication, isn't it? uv dash times vu dash. So dy dx will equal uv dash. Okay, so it's in brackets 2x squared minus 4, close brackets, in brackets. Now here we got 6 times 3 is 18. Or we need square brackets, don't we, because we've got brackets within brackets. So 18, 3x plus 5 to the power of 5, close with square brackets, and then it's plus, what have we got, 4x, and then in brackets it's going to be 3x plus 5 raised to the power of 6. 3x plus 5 raised to the power of 6. Okay, let's speed that up a bit and see what can be done. Well, not a lot really, but there is something we can do. We can certainly bring out the 18 out the front. So it would look like this. 18, 2x squared minus 4, 3x plus 5, raised to the power of 5, plus 4x, 3x plus 5, raised to the power of 6. Now there's a couple of things worth noting. Certainly we could factorise this quite a bit, even if it was just to divide both by 2 and take it out there. Then we could divide this by 2 and that would be legitimate. The other thing is there's common factors here as well, so we should probably deal with those. 3x plus 5 to the power of 5 is the highest common factor. So let's take that out and see what happens. We've got, oops, so 3x plus 5 raised to the power of 5, and then we're going to open up probably square brackets, and 18 bracket 2x squared minus 4 goes like that, and then plus 4x bracket 3x plus 5, close square bracket. So can you see that when I multiply that by that, I get back to that, okay? For example. Now what can we do? Well, we really should expand out here and see what's going on. Okay? So, let's take it to the next step. Let's just put a dy dx back in so we don't lose track of that. Equals 3x plus 5. Now, what have we got here? Well, we've got 18 times 2x squared is 36 x squared minus 4 lots of 18, or 2 lots of 18 is 36, and double that, you get 72, plus, what I've got here is 4x times 3x is 12x squared, plus 20x, just squeaking it in there like that. And therefore, dy dx is equal to, a bit of collecting of like terms to be done here, I feel. Let's have a look. I've got an x squared term here and here. That's an x term and that's just a constant. So it's going to be 36x squared plus 12x squared is 48x squared plus 20x minus 72. Okay, and also what I've noticed is I left out the power of 5 there, didn't I? So let's just put it back in, and that should be that example. Yes, I could take some common factors out there, numeric ones, but I'll leave it as is. On to our second example. Now this does look like a quotient rule problem, doesn't it? You've got an algebraic fraction here, so that could be u, that could be v, and away you go with the quotient rule problem. But you can get around using the quotient rule nearly always, and we can convert this to a product rule problem. And the way we're going to do that is to get this x upstairs, and we can do that because really that's x to the power of 1, isn't it? Well, I can bring that upstairs if I call it x to the power of not 1 but negative 1, so you're just changing the sign of the index downstairs. Okay, so now I'm going to rewrite this in calculus friendly form, and that means putting that in index form. Okay, so the square root of anything is just that thing raised to the power of a half, isn't it? So putting those ideas together, I can say that y is equal to x minus 1 to the power of a half times x to the power of negative 1. Okay, so now you can see that that really is in product rule form, where that is u and x to the negative 1 is v. Okay, so we know the it should be a familiar template now. If y equals uv, then the derivative of y equals uv dash plus vu dash. Okay, let's identify our u's and our v's. Well, certainly u is x minus 1 in brackets raised to the power of a half, and u dash would be, we'll bring the half down the front. We're using the chain rule now, of course, x minus 1, chain rule, otherwise known as a function of a function rule. Reduce your index by 1 and you're timesing by the derivative of what's in brackets. Now really I don't need to write times 1 down, but I'll put it there so you don't forget to multiply by what's the derivative of what's in brackets. Okay, now remember v is x to the negative 1, and there's no tricks to finding the derivative of that. You bring the negative 1 downstairs, well, without the 1 bit, don't need it, and reduce the index by 1. Okay, so we've identified our u's and v's. Now that means we can go straight to this line, dy dx equals, now look at the template, it says uv dash plus vu dash. Where's uv dash? Well, uv dash is right there, isn't it? So it's that times that plus that times that. So let's just write that down. Negative x to the power of negative 2 times, let's put it in brackets, x minus 1 raised to the power of a half, and then it's plus x to the negative 1 times, we're going to need square brackets here, a half, round brackets, x minus 1 to the power of negative a half, and close brackets. Now what have we got? Well, dy dx will equal, Okay, I've got a few things to think about here. Negative x to the power of negative 2. Well, that really means this. Remember, there is a clip on index laws and surds that you can look at, but you should realise by now that this is equal to negative 1 over x squared. Change the sign of the index, and that means you can take it downstairs. Okay, now what's this bit here? Well, that's x minus 1 to the power of a half. That's just, oops, let's put the pen on, just the square root of x minus 1, isn't it? And then we've got all this stuff here to worry about. So x to the negative 1, well, let's just write that as 1 over x times. You've got a half here, so that stays like that. Now, what's all this about? Well, remember, you've got a negative there, so negative a half means 1 over the positive half, using the index of a half. So that would really be 1 over the square root, because the square root means to the power of a half, doesn't it? X minus 1, like that. And we're nearly done, but not quite. Our final line would look like this. dy, oh, we've gone red all of a sudden, dy dx equals. Okay, so what we can do is bring this to be over the x squared. So negative x minus 1. So you always aim to be concise in mathematics. Plus, this bit's easy because it's just 1 times 1 times 1 over x times 2, so we call that 2x, wouldn't we, times that. Okay, so that's not too bad. We've got 1 over 2x square root x minus 1.